Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence.
Hey everyone, excited to dive into this topic today. Seems like we're tackling scaling laws for DiLoCo, distributed low communication training, right?
That's the one. I have a few thoughts about this one. I think we should delve into that more carefully.
Scaling laws always get me going. There's a promise of progress there, but it usually involves throwing more and more resources at the problem without actually fundamentally solving anything.
I agree with both sentiments, Dawn and Sarah. It's a double-edged sword. On one hand, these scaling laws, if they hold true, give us a roadmap, right? A way to predict how much bigger our models need to be, how much data we need to achieve certain performance levels. But on the other hand, it begs the question, are we just building bigger, more energy-hungry, data-dependent pattern recognizers? Or are we actually moving towards something resembling genuine intelligence?
Well, that's the million-dollar question, isn't it? I tend to be more optimistic. If this DiLoCo scaling holds, it does suggest that we're on a somewhat predictable path toward AGI, even if it's resource-intensive. Think about it. We've seen these scaling laws play out in other areas of deep learning. Bigger models, more data, better performance. It's a trend. And while I agree that pattern recognition is a component, the complexity of the patterns these models are recognizing is increasing exponentially. We're seeing emergent behaviors that weren't explicitly programmed in.
Emergent behaviors that are often brittle and unreliable. Sure, a large language model can generate seemingly coherent text, but it can also confidently hallucinate facts, perpetuate biases, and completely fail at simple logical reasoning. Scaling up might mask some of those flaws, but it doesn't fundamentally address them. It's like polishing a turd. It's still a turd.
Exactly. It's all about the underlying representation. These models are learning statistical correlations in the data, but they don't have a real understanding of the world. They can't translate between different coordinate systems. They don't understand cause and effect in the way a human does. Think about a self-driving car. It can be trained on millions of images, but if it encounters a situation it hasn't seen before, a weirdly shaped obstacle, an unusual lighting condition, it might completely fail, because it hasn't truly learned to see in the same way a human does.
Okay, I hear you both, but let's dig into the actual DiLoCo scaling. As I understand it, it focuses on distributed learning, which is crucial for handling these massive data sets and models. It's not just about throwing more data at a single machine. It's about efficiently training models across many machines. This scaling law, if accurate, gives us a way to optimize that distributed training process, reducing communication overhead and maximizing computational efficiency. That's a huge practical benefit.
And that efficiency has implications too, right? If we can train these models more efficiently, we can experiment more rapidly, try out different architectures, and ultimately, potentially discover more effective ways to represent knowledge. It's not just about making the current models bigger. It's about enabling us to explore the design space more effectively.
Explore the design space of what? Of bigger, more complex neural networks? I'm not convinced that's the right design space to be exploring. I think we need to be looking at fundamentally different approaches, like neuro-symbolic AI, where we combine the strengths of neural networks with the strengths of symbolic reasoning. We need systems that can learn from data, but also reason logically and manipulate abstract concepts.
Neuro-symbolic is interesting, but it's often brittle in its own way. The symbolic part needs to be handcrafted, and it can be difficult to adapt to new situations. I still think the key is in figuring out how to represent space and time in a more fundamental way. How do we build AI systems that can understand the relationships between objects in the world, not just recognize them?
Okay, so let's break this down. Let's say this DiLoCo scaling law accurately predicts that, with X amount of data and Y amount of compute, we can achieve Z level of performance on a specific task, like, say, complex question answering. What are the implications, practically? What are some real-world applications that would benefit from that level of performance?
Well, immediately, I think of advanced medical diagnostics. Imagine an AI system that can analyze medical images, patient history, and the latest research to accurately diagnose diseases with a level of precision that surpasses human doctors. That would require a huge amount of data, a very complex model, and, crucially, the ability to reason about complex relationships between symptoms, test results, and potential diagnoses.
And that's where the symbolic reasoning comes in. It's not enough to just recognize patterns in medical images. You need to understand the underlying physiology, the causal mechanisms of disease. You need to be able to reason about the implications of different treatments. Deep learning can help with the pattern recognition, but it can't do the reasoning.
Exactly. Think about drug discovery. It's not just about finding molecules that bind to a specific target. It's about understanding the complex interactions between the drug, the target, and the rest of the body. It's about predicting side effects, optimizing dosage, and understanding the spatiotemporal dynamics of drug delivery. That requires a much deeper level of understanding than current AI systems possess.
But even in drug discovery, deep learning is making huge strides. AlphaFold, for example, has revolutionized protein structure prediction. That's a massive step forward, and it's entirely based on deep learning. It's showing that these models can learn incredibly complex relationships, even at the molecular level.
True, but AlphaFold is still limited. It can predict the structure of a protein, but it doesn't necessarily understand the function of that protein or how it.
And it's trained on a massive data set of known protein structures. What happens when you encounter a completely novel protein with a structure that's unlike anything seen before? The deep learning model might struggle, whereas a system that understands the underlying principles of protein folding might be able to make a more informed prediction.
It's like trying to understand a sentence by memorizing all the words in the dictionary. You might be able to recognize the words, but you wouldn't necessarily understand the meaning of the sentence. You need to understand the grammar, the syntax, the context. You need to be able to translate between different levels of abstraction.
Okay, I get the point. Deep learning has limitations, but let's not throw the baby out with the bathwater. The scaling laws suggest that we can continue to improve these models and that those improvements will lead to real-world benefits. Maybe it's not AGI, maybe it's just incredibly powerful narrow AI, but that's still valuable.
Absolutely. And I think the DiLoCo scaling is also important in a practical sense because it relates to costs. If we can understand these scaling relationships better, we can make better decisions about where to invest our resources. Should we be focusing on building bigger models or on developing more efficient training algorithms? Should we be investing in more data or in better data annotation? These are crucial questions, and the scaling laws can help us answer them.
But what if the scaling laws are misleading? What if they only hold true up to a certain point, and then the performance plateaus? What if the cost of acquiring and processing more data becomes prohibitive? We need to be careful about extrapolating these laws too far.
And what if the fundamental limitations of the algorithm prevent us from ever achieving true intelligence, no matter how much data we throw at it? It's like trying to build a skyscraper on a weak foundation. You can keep adding more stories, but eventually the whole thing will collapse.
So, what are the alternatives? What's the foundation we should be building on? Neuro-symbolic AI, spatiotemporal reasoning? What are the concrete steps we can take to move beyond the limitations of deep learning?
Well, from my perspective, I think we need to be looking more closely at the brain. How does the brain represent knowledge? How does it learn? How does it reason? We need to be incorporating those principles into our AI architectures. Things like plasticity, synaptic scaling, hierarchical organization. These are all crucial features of the brain that are largely missing from current deep learning models. For example, the brain's ability to quickly integrate diverse sensory modalities into coherent representations could suggest ways to improve LLMs' understanding and use of multimodal data for reasoning.
Yes, exactly. And that's where the neuro-symbolic approach comes in. We can use neural networks to learn from data, but then we can extract symbolic representations from those networks and use them to reason logically. We can build systems that can both learn and reason, combining the best of both worlds. I've been reading about formal knowledge representation. Maybe the key to truly intelligent systems isn't more complex neural nets, but smarter ways of representing and manipulating knowledge.
I think we need to focus on building AI systems that can understand the relationships between objects in space and time. Systems that can reason about cause and effect, that can predict the consequences of their actions. We need to develop new algorithms that can translate between different coordinate systems, that can represent knowledge in a way that's inherently spatial and temporal. And the algorithm needs to be able to translate between different coordinate representations. If the model cannot effectively link different coordinate systems, it risks becoming a clever pattern matcher without true understanding.
And from my perspective, we need to continue pushing the boundaries of deep learning. We need to explore new architectures, new training methods, new data sets. We need to understand the scaling laws better, and we need to figure out how to overcome the limitations of current models. Maybe it means incorporating some of these neuro-inspired principles. Maybe it means developing entirely new approaches. But we need to keep experimenting and pushing the limits of what's possible. A detailed analysis of the DiLoCo scaling law would be crucial in predicting potential model architectures suitable for tackling tasks of increasing complexity, as well as forecasting the requirements of computational resources and data storage necessary to push towards AGI.
So, let's talk about future research directions. From my perspective, I'd love to see more research on the relationship between network size, learning speed, and performance in these distributed learning systems. How does the brain achieve such remarkable learning efficiency with relatively limited resources? Can we learn from those principles to design more efficient AI systems?
I'd like to see more research on neuro-symbolic AI. How can we effectively combine neural networks with symbolic reasoning systems? How can we extract symbolic representations from neural networks in a way that's robust and meaningful? How would a neurosymbolic algorithm handle the kinds of abstract reasoning tasks that currently seem to rely on the implicit representations learned by deep networks?
I want to see more work on spatiotemporal reasoning. How can we build AI systems that can understand the relationships between objects in space and time? How can we represent knowledge in a way that's inherently spatial and temporal? How can we build systems that can reason about cause and effect, that can predict the consequences of their actions? Specifically, I think the lack of an explicit methodology for translating between coordinate representations in current deep learning models is a major issue.
And I want to see more research on the scaling laws themselves. Do they hold true for different tasks, different architectures, different data sets? How can we extrapolate these laws to predict the performance of future models? What are the limitations of these laws, and how can we overcome them? How does the DiLoCo scaling law account for the trade-offs between model complexity and data efficiency? Is there a point where the cost of acquiring and processing more data outweighs the benefits of increased performance? And does this scaling law account for this inherent limit?
Those are all excellent points. It's clear that there's still a lot of work to be done before we achieve true artificial general intelligence. But I think we're making progress, and I'm optimistic that we'll continue to see breakthroughs in the years to come.
I'm a bit more skeptical, but I agree that it's important to keep exploring different approaches and pushing the boundaries of what's possible.
I think the key is to focus on building AI systems that truly understand the world, not just recognize patterns in data.
And I think the scaling laws provide a roadmap, even if it's a bumpy one, towards that goal.
Well, that's all the time we have for today. Thanks for joining us on Cognitive Spirals. We hope you enjoyed the discussion.